Hello, everyone. I'm happy to see so many people have joined. Sorry about the little technical issues. We'll get that fixed for next time. So today we have Robert Szafarczyk Szafarczyk, from University of Copenhagen, who is going to speak to us about lifting schemes to the sphere. Thank you.
Yes, thank you very much for the introduction. And thank you for the opportunity to speak. So yes, I will talk about lifting schemes to the sphere, and I will soon explain what that means. So the general goal is to obstruct rings or schemes from being defined over the sphere spectrum. And so the first thing I'll do is, well, tell you what it means, and also tell you some approaches which are in the literature of obstructing this. And then what I will focus on is a different approach using what is called delta hat rings. So first we will start with the affine case, defining delta hat rings, and using this to say something about Z mod n or Z adjoint some root of unity. And then I will move to delta hat schemes. So I will define them and use this obstruction for things like group schemes or projective schemes. Okay, so first let me tell you what I mean by a lift. So if we are given a just discrete commutative ring, then it lives over the integers in commutative rings. But if we move to higher algebra and we allow for commutative ring spectra, then we get another point in our diagram, which is the sphere spectrum, which maps to the integers, which maps to R. So then a natural question is, if there is a commutative ring spectrum SR such that completes the square in a way that this is a push-out. And in commutative algebras, push-outs are computed by tensor products. So what we're asking for is a connective commutative ring spectrum such that this base change is R. So this is what I call a lift to the sphere of the ring R. Okay? So this is the question we are interested in is for rings, but let's first see what happens if A is just an abelian group, because then, and we just ask for a spectrum SA satisfying that base change to Z is A without any ring structures. And then we can construct this SA by, well, for the abelian group, we can choose a free resolution, two-term resolution. And then what we can just do is replace those Z's by the sphere spectrum. Here there's some matrix defining this map. We can also choose, because homotopy classes of maps between the sphere spectrum is just integers, so we can choose a lift for this matrix and then take the cofiber. And then obviously by base change, if we base change this cofiber, then since base change commutes with collimate, we just, well, go back to this diagram and the cofiber of this diagram is just A. So we've lifted any abelian group to the sphere spectrum. So for example, well, if our abelian group is Z mod n, then our lift will be S mod n. If our abelian group is Z adjoint root of unity, then I will call the spectrum S adjoint root of unity. And then, well, we can also take some polynomial algebra and quotient it by some relation. And I can also do it here. And it turns out that those lifts at the level of spectra are actually unique in the homotopy category. So in this construction, we've chosen a resolution of A. So a priori, this spectrum SA depends on this resolution and on the lift here. But in fact, if we just care about the object itself, then it is well defined up to equivalence. So there's a unique lift in the homotopy category spectra. It is not functorial though. So the lift is unique, but there's no functoriality. But still, this is okay for us, because now our first question, where we ask for lift of a commutative ring, then as an abelian group, we know how it lifts. So the only thing to give more is a ring structure on this SR. So our question 1 becomes equivalent to question 2, which is just, are there infinity structures on SR, which give you the ring structure on R? So this is the setup. Are there any questions?
Sorry, hi.
Yeah.
Could you clarify why it's not functorial? Because if it's unique, then surely like it will preserve compositions, right?
Well, the object is unique up to equivalence in the homotopy category. But if you try lifting maps, then even in just in the homotopy category, then there is a problem with two torsion that after inverting 2, you can get a functor to the homotopy category via those lifts. But if 2 is not invertible, then a map can have 2 different lifts, for example.
Okay, so in that case, it wouldn't be unique then, or I don't want to.
The map, yes.
Okay, yeah, okay.
Lists of maps are not unique.
Okay, thank you.
Yeah. Okay, so what we want to do, well, so this question is, we'll try to answer this question negatively. So we are focused here on obstructing those infinity ring structures, so proving that they don't exist. And the first examples, which I want to talk about, come maybe from algebraic topology. And the first one is that S mod 2 has no unital multiplication. So there's no ring structure whatsoever. And how to see this is like a classical fact proof via Steenrod operations, because if we had a multiplication like this, which was unital, then inserting a unit in either of the coordinates gives a splitting. So this is my multiplication, and this is like unit times identity. So then if I multiply something with the unit, I get the same thing. So this defines a splitting. And we can show that this splitting cannot occur because on F2 cohomology, we have the guy on the left is some t is generated by some t, and then the first Steenrod square of t. And on the right, we have some, I'm just calling generators, so x, y, and t. And here by the QNet formula, we would have x times y. We would also have SQ1x times y and x times SQ1 and y. and also SQ1 X, SQ1 Y. And now this splitting would imply that the right thing embeds into the left thing. But by degree reasons, SQ2 of T is 0. But on the other hand, SQ2 of X times Y, like a formula for the tensor product, would be SQ1X times SQ1Y, which is not 0. Okay, so this shows that this map, well, there cannot be S mod 2 is not a retract of S mod 2 tensor S mod 2, and this cannot happen if you have a unital multiplication. Well, this always happens when you have a unital multiplication, so S mod 2 has no unital multiplication. So this is using Steenrod squares. But then you can also show that S mod 3 can have no homotopy associative structure, and this uses Toda brackets. S mod P is not AP, and this uses some higher Toda brackets or Massey products. And this AP, so AN is like the higher the N, the more associative the multiplicative structure is. So the A infinity would be fully associative, which is the same as E1. So maybe let me remark this, that, well, E1 is A infinity, which is like fully associative. Okay, and then E infinity is like fully commutative. By the way, I maybe forgot to mention at the beginning that I'm going quite quickly, so if you're taking notes, it's probably hard to follow. I will send the slides and they will be available after the talk. So I will soon use those things. So E1 is fully associative, then if we go like EM is like more and more commutative until we reach infinity, which is fully commutative and associative. So those results can be obtained by some algebraic topology, let's say. But there's also a result due to Lawson that, well, we already know S mod P cannot be fully associative. And Lawson, by an argument of his, one can show that S mod P to the N is never fully commutative. Okay, but so they cannot be commutative, but maybe they can be highly associative. So, and this research into what associative structures you can put on S mod P to the N's was quite well studied. For example, yeah, there have been constructed by Oka or recently by Bhattacharya and Kichlo. But in general, it was conjectured that they can never be fully associative, which in fact turns out to be very wrong. And there's a recent result of Robert Bertrand, which says that S mod P to the N can be arbitrarily EM if you choose N big enough. So we know it cannot reach full commutativity, but it can get more and more commutative. Again, the second obstruction for lifts, which exists in the literature, is via THH. So there's a result of Schwenzel, Vogt, and Waldhausen that Z adjoint the imaginary unit cannot be fully associative, so E1. And how you do it is that suppose there is a lift, E, and then we can use some base change formulas for THH. So if you don't know what THH is, it's like topological Hochschild homology, but I don't use anything about it. I just need that it satisfies some base change formulas and that we can compute it. So if we start with THH of Z adjoint I, then I can rewrite Z adjoint I by assumption as E tensor with Z. And then THH satisfies a base change formula that THH of a tensor product is the tensor product of THHs. So I can write this. And then I observe that THH of Z is a Z-algebra. And if I have a Z-algebra, then I can write it as Z over Z times relative to Z with itself, right? And if I do it, then I can rebracket and look at this guy, which is THH of E base change to Z. And then THH satisfies another base change formula that this becomes equivalent to THH of E times Z, but now not relative to the sphere spectrum, but relative to the integers. So E times Z becomes Z adjoint I, and THH relative to the integers is just Hochschild homology. So what we get in the end is that topological, if we assume existence of a lift, then we can express topological Hochschild homology of Zi as Hochschild homology tensored with topological Hochschild homology of the integers. And this is a contradiction because we can compute both sides. We can compute both sides, and we just see that the guy on the right is just much bigger than what we get on the left, which implies that there cannot be a lift. And this approach also works for S mod P. So we can show that S mod P is not E1 by computing THH, but it does not for S mod P to the N. For S mod P to the N, we can compute both sides, but they turn out to be equivalent as spectra. Okay, maybe are there more questions up to this point? If not, then I will move to the third obstruction, which is the main player in this talk. And this uses a concept of a delta ring. So let me first recall you the definition. So a delta ring is a commutative ring R plus a function delta. So it's just a function on underlying sets, which satisfies those three axioms. So like on 0 and on 1, it takes value 0, and then has some addition formula and some multiplication formula. It's kind of similar to a derivative, to a differential, yeah, because, well, there is this additional term, and here we have those powers and this term, but this, for example, looks like a Leibniz rule. And when we know what a delta ring is, I'm actually more interested in delta hat rings. So a delta hat ring.
Before you go to the next definition, there's a question in chat. What is the P in the definition of delta ring?
Oh, P, yes, good question. P is a prime, fixed prime. So it's kind of an abuse of notation, but whenever we say a delta structure, then there's some P hidden in the context. So for example, here, right, so now I want to define a delta hat ring. So a delta hat ring is, again, commutative ring R, but now I put a delta structure on each P completion of R. So for prime 2, I would have on the 2 completion of R, I would have a delta structure where everywhere I put 2. Right? On the 3 completion, I would have 3 everywhere, and so on.
So does the prime need to be invertible in the ring? Is there any connection between, like, assumptions?
Yeah, so so first remark is that those delta structures, like for different P's, do not talk to each other. They're completely unrelated. And second thing is that note that if P is invertible in R, then the P completion is 0, because I take quotients by P to the n and then take a limit. So the quotients are 0, so the limit is also 0. So this delta structure is only on, well, it only matters if P is not invertible. Right? So let's see some examples. So Z is the initial delta ring, and there's only one delta structure on Z, or ZP, which is given that on an integer n, I have this formula, n minus n to the p over p. And why I can divide by p here is because, well, after mod p reduction, on fp, the Frobenius, which is given by power p, is the identity. So this guy vanishes at fp, which means that it's invertible by p. So this formula makes sense. So this is integers, and then if I want to, say, put a delta structure on a polynomial ring, then I already know what it does on the integers. It must be this formula. So the only thing to choose is its value on x. It's the value of delta on x. Because remember, delta satisfies those addition formulas and multiplicative formulas. So if I know the value on x and on every integer, then I can deduce from it the value on every polynomial. And it turns out that you can just choose anything for delta of x. There's no constraints. Maybe in general, for a p-torsion free ring, a delta structure always looks like this. So phi of x minus x to the p divided by p, where phi of x is what I call a Frobenius lift, which just means that modulo p phi looks like the Frobenius, like power p. And this actually defines a bijection. So for a p-torsion free ring, a delta structure always comes from a Frobenius lift, and every Frobenius lift defines a delta structure in this way. So there's a bijection between Frobenius lifts and delta structures on your ring. And if you want to, and you can also say it more generally, deleting the p-torsion freeness assumption, but then you need to be careful, and instead of so delta structures are still the correct thing to do, but then instead of a Frobenius lift, what you want is a derived Frobenius lift. So you need to take derived mod p reduction, but we will only stay in the realm most of the time in the realm of flat rings. So you can just think of a delta structure as a Frobenius lift. So maybe here phi, So phi is a ring endomorphism of R. And this also goes back to this first example because the only automorphism of the integers is the identity. So we know that this must be the formula. Okay, and why I have introduced those delta hat rings is because we have the following theorem due to Thomas Nikolaus that if R is a commutative ring, then a lift of R to an infinity algebra induces a delta hat structure on R, in fact, in a factorial way. So how we will use this theorem is kind of in the inverse direction, which means that if we're able to prove that there's no delta hat structure on R, then we deduce that there is no lift. So SR has no infinity structure. Okay, and in the case of Z mod P to the N, we can easily check that there's no delta hat structure. Well, Z mod P to the N is already P complete and other primes are invertible. So the only structure is just, the only thing we need to put on it is a delta structure for the prime P. But then we can see that on one hand, delta of P to the N, since P to the N is 0. But we can also write it by our formula that it's P to the N minus P to the NP over P. But this equals to P to the N minus 1, which is not 0, times something which is invertible. So we get a contradiction. So Z mod P to the N cannot have a delta hat structure, which means that S mod P to the N is not infinity. So we kind of recover the result of Lawson. Are there questions?
Sorry, could you just repeat why it's the only delta structure like this one that you gave? Like it's the only thing you have to check.
Well, so I'm checking for the Z mod P to the N example.
Yeah, exactly.
So I'm checking that it's like this. Assume there is a delta structure on Z mod P to the N. Then delta of P to the N is 0. But also P to the N is an integer. And I know that for integers, there's a unique delta structure, which is given by this formula.
Okay, yeah, that's the point. Yeah, thank you.
Okay, and I want to point out that assuming this theorem, which is actually not that hard to prove, I will sketch a proof in a second, but assuming this theorem, proving that S mod P to the N has no infinity structure, it took us one line of computation. And this computation was purely algebra, was purely one algebra, right? So the initial question is about higher algebra, and it has a lot of topological input in it, as we saw with like Toda brackets. But after we know this obstruction, proving something about this higher algebraic question boils down just to some computation in one algebra, which I find quite surprising. Okay, and another example, another computation we can do is with the Z adjoint Q primitive root of unity, where Q is some power of P. So how you can present this ring is by the polynomial algebra on one generator quotiented by some Eisenstein polynomial. So for example, Z adjoint I, well, normally you write it as Z adjoint X over X squared plus 1. But after some change of coordinates, this is the same thing as Z adjoint X over this X squared plus 2X plus 2, and this polynomial is Eisenstein. So 2 divides all coefficients apart from the first one, and 2 squared doesn't divide the last one. And if we know that, then we can prove that there's no delta hat structure on the P completion. So we P complete where P is the same prime as here. And then if we have a delta structure, also for the same prime as here, then we can compute that on one hand, delta of E of X is 0 because we've killed E of X. But if we write the formula here, then you can check that, well, since the Eisenstein polynomial has a lot of coefficients which are P, then what it turns out that if you take modulo P, then everything simplifies, and what you're left with is this term, E of 0 over P. But now E was Eisenstein, so E of 0 is divisible by P, but is not divisible by P squared, which means that this term here is invertible, and in particular not 0. So again, we get a contradiction, and hence there is no commutative ring spectrum of the form S adjoint root of unity. So this is how we use this abstraction. And here there's a little remark that if we invert P, so remember inverting P kind of deletes the P completion. So removes this delta condition kind of at the prime P, then this ring will actually be étale, and there's a celebrated result of Lurie which says that étale algebras always lived. So the only obstruction is at prime P, and we can see it using this delta hat structure. Okay, so now let me just quickly tell you where those delta hat structures come from. So if we have a lift SR, so this is an E-infinity algebra, and every E-infinity algebra has what is called a Tate-valued Frobenius. So it's a map from SR, a ring map from SR to SR Tate construction of CP. But in this case, in this particular case of ring spectra looking like a lift of an of this form, the Seagull conjecture implies that the Tate construction is just the P completion. So after base change, we get a map from R to the P completion of R. And this map can be checked to lift the Frobenius on the P completion of R. So the delta hat structure comes from the Tate-Frobeni on the lift. Okay, so this was about delta hat rings, and now I want to get to delta hat schemes. So maybe if there are questions, it's a good moment. Okay, if not, then, well, we want to extend this abstraction to schemes. So first, let's extend the definition of a delta hat ring to a scheme. And, well, the plan is, if you imagine a scheme is just something glued from rings, then a delta hat scheme should be a scheme which is not glued from rings, but glued from delta hat rings in a compatible way. So the first thing to check is that if we have a delta hat ring and an element in it, then we want the delta hat structure to induce a delta hat structure after inverting F, which means that if I have a delta hat, well, if I have my delta hat ring, then I choose a smaller open in it, then I should get a delta hat structure there. So what we want to do is put a delta hat structure on after inverting F. So we need to give a Frobenius lift. So by the universal property, we need to just prove that phi of F is invertible in the P completion of R with F inverted. And this is true because phi of F is F to the P modulo P. And well, F to the P is invertible and we work P completely. So if something is invertible after a mod P reduction, then it's invertible globally. So this gives a delta hat structure on after localization. And one can also show that delta hat rings glue. So if I have several of those Fs which generate the unit ideal, and I have delta hat structures on all localizations which agree on intersections, then I will get a delta hat structure globally. This is just a formal proof that R is just given as a limit. So if we can glue and we can localize, then, well, it seems reasonable to define a delta hat scheme as a scheme together with compatible delta hat structures on global sections of each affine open. So it really looks like a scheme glued from delta hat rings. Okay, so this is the delta hat side of the picture, but if you want to lift schemes, then I should tell you what does it mean to be a scheme in higher algebra. And this again, if a scheme is just something glued from rings, then a spectral scheme would be a scheme glued from E-infinity algebras. So how to do it properly is that if we're given an E-infinity algebra, then we can take its pi 0. This is just a discrete ring. So we can take the spectrum of it and then define the structure sheaf to, on a distinguished open, give me the localization of the whole algebra. And we call this the spectrum of E. And then a spectral scheme is, well, a space locally, a ringed E-infinity ringed space locally equivalent to spec E. And well, we say it's connective if those local pieces are for connective E-infinity algebras. So the main difference between spectral algebraic geometry and algebraic geometry, at least for our purposes, is that pullbacks are computed not as tensor products, but as derived tensor products, and sheafification as well as a derived limit. But yeah, don't worry too much about spectral algebraic geometry. It's just so that I can say what it means to lift a scheme. So if we're given a scheme X, then a lift to the sphere spectrum would be a connective spectral scheme XS, such that we have the following square, and it is a pullback. So this, right? We first start with this, and then we ask for a lift of X to the sphere spectrum. And we introduced delta hat schemes as things glued from delta hat rings. Spectral schemes are things glued from infinity algebras. And we have the theorem that obstructing rings to lift is via delta hat structures. So then one can imagine that the theorem glues as well. And we get the following theorem that lifts of schemes induce delta hat scheme structures on X as well in a functorial way. Are there questions? If not, then we will now do some examples of schemes. So this functorial way is really useful here because not only we can obstruct schemes from lifting, but we can obstruct group schemes from lifting. Because a group scheme is just, well, a scheme plus some multiplication and some unit and so on. So also this if the group scheme structure lifts, then the multiplication also lifts, right? And so on. So the first proposition is that GA, the additive group scheme, has no delta hat group scheme structure. So by the theorem from the slide before, it does not admit a lift to the sphere. There's no spectral group scheme which would lift GA. But on the other hand, like GA is just spec of Z adjoint X, which lifts as spec SX. Because SX is like the monoid ring over the natural numbers. So as a scheme, there's no problem, but there's a problem with the group structure. And how to prove this is, well, suppose we have a delta hat structure on ZX. And what it means for it to be compatible with the group structure is that the commultiplication on the level of rings preserves the delta hat structure. And the commultiplication in the case of GA is given by sending T to X plus Y. Okay, and this is just asking for an element. So I just look at the prime 2, and well, this would imply that there is an element F which satisfies this formula. But this is impossible because if we take modulo T, this equation, then on the right, we have this xy term, which is non-zero, because neither here nor here can be any xy terms. So this xy term is still there. But on the left side, we cannot have any xy term because, well, if there's a square here, then we would get 2xy, but 2xy is 0 modulo 2. So we cannot have such a delta hat structure compatible with this commultiplication, which means that GA does not lift as a group scheme. On the other hand, GM has a very nice lift because GM lifts as the group ring over the integers, spectrum of the group ring of the integers, and the commultiplication. So the commultiplication now sends T to X times Y, and this map can be seen as just the diagonal. It's induced by the diagonal on the monoid Z. So since it comes from Z, it also lifts to the sphere. But what we can check, so this lift induces a delta hat structure, a delta hat group scheme structure on GM. And what we can check is that it's the only one. So again, we get some F which satisfies some equation. This is now the equation for the multiplication, right? Delta of xy is x to the p delta y, delta x y to the p, and then this. And if F is non-zero, then you can check taking some modulo high enough power that you get some equation like this, and then you just look at degrees and you get that F must be 0, in fact. So I just want to say that, again, you just, using this obstruction, you just get some polynomial equation and you just check that it cannot hold. So the last example I want to mention is projective schemes. And here, well, A1 is just spec of S of x, so Z of x. So it has a lot of delta structures, as we said. But a delta hat structure on A1 then induces a delta hat structure on AN. And then if you want to get a delta hat structure on PN, well, PN is glued from some copies of AN. And we also have a map like this, the projectivization. So we say that this delta hat structure on A1 is coherent if it glues to a delta hat structure on Pn, and the projectivization map is a map of delta hat schemes. So what I want to say is that we have a lot of delta structures on A1, but we're looking now only at those which are reasonable to define Pn. And it turns out that there's only one reasonable delta hat structure on A1. And this is the canonical one. And why I was talking about this is because if I want to abstract some projective schemes from lifting, then it gets hard. So at least there's a lot of options. So instead of abstracting any lift, I want to abstract, well, okay, so here, instead of, if I have a projective scheme, instead of abstracting any lift of Z, I want to abstract only Z lifting to a closed subscheme of this spectral version of Pn. Because like here I just say that this lift of Pn can be just constructed in the same way that we've constructed Pn by gluing copies of An. This just works over S as well. And then the one result is that elliptic curves do not lift to this PNS. So elliptic curves are cut out by such an equation. And what the result tells you is that in this spectral scheme, well, you don't have any subscheme cut out by such an equation.
May I ask a question?
Yes?
So here, when you say Pn, you mean Pn where you consider delta hat structure given by the zeros delta hat structures on H(n), right?
Yes.
Okay, but you don't claim that there are no other delta hat structures, right?
Yes. So my claim is that this structure given by 0 is the only reasonable one.
But
And then,
do I
yeah.
understand correctly that like on the previous slide you kind of only try to find such a lift which comes from gluing Pn from copies of ANs, and considering
Yeah.
on each AN you consider kind of the same
Yes.
kind of the
Yes,
same
exactly.
okay, but
Yeah.
it's but I mean the
If-
gluing maps between ANs are typically given by, I don't know, something like x goes to x to d minus 1 or something like this. So one would expect that if some gluing exists, then you should consider kind of different polynomials for different delta structures, for
Yes.
different copies of ANs.
Yes, so in theory, there could be different delta hat structures on ANs which glue to a delta hat structure on PN, which does not come from a single delta structure on A1. Yeah.
Okay, thank you.
And then by elliptic curves do not lift, I mean that they do not lift to this kind of canonical lift of Pn. Okay, and yeah, this is it. Thank you for listening.
Thank you very much. Everyone feel welcome to unmute and thank Robert for a great talk. Is there any questions?